All right, everybody, let's get started. This is it. This is our last week together, at least in this semester. How many steel folks do I have next semester? I'm just curious. Okay. All right, cool. So I'll see most of you next semester. All right. Hopefully everybody had a good break. And you hopefully saw my email yesterday where I've got the project submittal 2 graded. All in all, I think everybody did very well. So not a whole lot to say. I think y'all did just fine. Okay, so I typically like to start the presentation or the announcement slide after Thanksgiving break with a couple housekeeping items because we are down to the wire. I mean, this is it. This is the end of the semester. So I'll mention a couple of things. First off, the attendance grades on Blackboard are currently up to date. The project is graded, the grade reports are distributed, and then all the outstanding homework is graded, and there's no homework due today. We do have a homework due on Wednesday, okay? Everybody okay with that? All right, so has everybody got the code? Okay, so I want to talk about our remaining housekeeping for the class, and I like to center my discussion around this because I imagine that's what everybody sort of thinks about in terms of finishing out the class, which is their grade in the class. So let's go through this. So your grade in the class is developed based on the attendance, the project grade, the homework, and the 3 exams. So where are we at right now? The attendance is up to date other than this week, right? We have attendance today, Wednesday, and Friday, and that'll be your attendance grade for the semester. The project, it's graded. The grades are posted to Blackboard. As for the exams, we have 2 exams done, 1 exam left, and that exam is next Monday, right? So you all got my at-home game spreadsheet, so you all can play the at-home game and see what grade you need to get on the final in order to get some grade in the class and whatnot, so you all know the deal there. Okay, so let's wrap it up. Where are we going from here, okay? So right now for the homeworks, everything should be graded and up to date up through homework 8.5. We have 2 more required assignments, okay? We have homework 9.1, which is due Wednesday, and homework 9.2, which is due Friday. I'll go ahead and tell you homework 9.2 is pretty short. It's a pretty short assignment. Homework 9.1 is a little bit longer because it's a full-blown matrix analysis, whereas homework 9.2 is really just a small piece of one. And then I do have 1 bonus assignment, which is the course eval. I just want to see that you've done it. You could say I'm the worst professor ever, but I do want to see that you did it. I really do appreciate any suggestions that you have or any feedback that you have for the next time that I teach this class. So if there's anything that you see that should be improved in the class, I really will take it to heart. So in order to encourage that you've done it, if you upload a screenshot that you did it, I don't want to see what you said, just that you did it, I'll give you 10 bonus homework points on top of your homework average. And I had to do a little bit of configuring this weekend on Blackboard to make that work. So I think it's working well now. Okay. In terms of the remaining lecture schedule, so what we're going to be talking about today and Wednesday is matrix analysis. So I told you that we're going to cover bars and trusses. So the theme of this week is to take matrix analysis and look at trusses. And so it's really an apt time to talk about it because now what we can basically do is fully explain what Masthand was doing when you clicked the Analyze button and analyzed a truss. Okay, and that's going to be the goal this week. Okay, that's Monday and Wednesday. Friday, we're going to review for the exam. Okay, so it's just like any other exam review day. As for the exam's going to be on Monday, December 9th, from 10:15 to 12:15 p.m. It's not a comprehensive exam, and it's going to be similar logistics and operations. One thing I'll tell you is that I am designing the exam to be 50 minutes long, but I am contemplating, I usually do like a series of conceptual questions and then 3 problems. I'm contemplating doing 4 problems, not because I'm trying to give you more work, but it's mainly for your benefit. The thing about influence line problems is they're either right or they're wrong, so they give very little room for partial credit. but if I throw another problem in there, that'll take the sting off. So I'm trying to give you all some space for partial credit. Okay, and that's the review slide for tomorrow, or for Wednesday. All right, does anybody have any questions about the logistics so far? And did everybody get the code? Did everybody get the code? Let's see if they didn't get the code. You got it? You got the code? Okay. Okay. All right. Couldn't help it. Okay. All right. So does anybody have any questions? Everybody good on logistics? Okay, let's get started. Okay, so what we're going to be doing today is taking this hullabaloo that we talked about with bar analyses and look at trusses. My goal with the education of matrix analysis is, and I mean, I want to be clear, I could devote an entire course to just matrix analysis of structures. We have a course at Marshall dedicated to just that. It's called Finite Elements. So if you ever take Engineering 570, that's what this is. So I can't devote an entire, I can't explain everything. What was that?
I think that was our cue to go home before we explode.
I think it was just the HVAC system being cantankerous. But I'm going to press on. So, but that was distracting. I'll give you that. But like going back to matrix analysis, I can't show you everything, but what I want to show you is enough so that you have a general understanding of what these software programs do. And if you're interested in learning about some much more rigorous and much more a bigger picture of computer-based structural analysis, I would take Engineering 570 because it's a great class. Okay, so let's just sort of recap, because I know it's been a while since we've talked about this. And this is the way that I sort of broke up matrix analysis for our purposes in this class. And I sort of broke it up into two parts, okay? So the first part is the formulation of the stiffness matrix. And so what we had done is we had said, okay, we're going to write these spring matrices or these stiffness matrices for each element. Then we're going to engage in this process called assembly to get to here, right? And then what we're going to do next is we're going to assemble the force vector, right? So we take our stiffness matrix, we take our force vector, and that's parts 1 and 2. What do we do in part 3? Well, in part 3, what we do is we say, okay, let's knock out the rows and columns for the boundary conditions to get KR. Let's knock out the rows for the boundary conditions to get FR, and then invert that times this to get the displacements. Okay? And that's essentially part 3 is just solving for the displacements. And what do we do in part 4? The theme of part 4 is back substitution. So we take those displacements, plug them back in to get our reaction. So this is the reaction step. And this is to get the individual forces inside each member. And so when it's all said and done, what do you get out of steps 3 and 4? You get the displacements everywhere. You get the reactions everywhere. You get the forces in every member. Problem's done. Okay, and we've solved for literally anything and everything that we would want to solve for in this problem. Okay, so one thing that might, one question that might come up is, well, this is the matrix analysis that I presented for bar systems. How does it change for trusses? Okay, well, one thing that happens with trusses is we have to sort of take a little bit of a pit stop right here. Okay, so what we have to do right here is we have to first off transform each of these and then assemble them. And the notation, and you're going to understand why here in a bit, is that we end up starting off with this KE prime, and then we have to transform it into KEs before we assemble that. And then the only other thing that changes is this step right here, okay? Because what we end up saying is that, okay? In other words, we throw in another little matrix right here. But if you really want a big picture as to what changes between bars and trusses, that's it. Period. Okay? And this T matrix, this transformation matrix, is really just a fancy way of organizing some trigonometry. If you understand that, then you understand how to analyze trusses. But don't worry, we're going to digest what's going on here all throughout today's lecture. Okay? Everybody good with that? Now, don't forget that we are going to be doing matrix multiplication, and we're going to be doing matrix operations, so let's just make sure we are familiar with a lot of this stuff. So if I have a matrix or a vector, I can do a series of things to them. I can add them. I can perform scalar multiplication. I can multiply the matrices, provided they're dimensionally congruent. And then a couple things about matrix multiplication. It's generally not commutative. In other words, A times B does not equal B times A. And so that's like particularly true, for example, like in this step, like we can't just flip that around. Like it has to be in this order. And you'll see why here in a bit. There is one case, or two cases of commutativity. If one of those matrices happens to be the identity matrix, then it doesn't matter which direction you multiply, or you can do A times I or I times A, it doesn't matter. And then the other special case is if one is the inverse of one another. Like if B is the inverse of A, you can do AB or BA and get the identity. We can invert a matrix. Take a linear algebra class to learn all about the various algorithms on inverting matrices. We're just going to surrender to the software in here. There are some closed form formulas for 2x2s and 3x3s, but past that it just gets ridiculous and it's better to just let the software do it anyways. And then finally we can transpose a matrix. And remember what transposing is? That's when you flip it about the main diagonal. Remember that? Where you have that main diagonal and you just flip the terms. We are going to see transposes today, and we won't see a symmetric matrix today. A symmetric matrix is if a matrix equals the transpose. Well, I guess that's not true because stiffness matrices, spring matrices, they're all symmetric. So, but I'm getting ahead of myself. Okay, sound good? Now, what is going to be pretty important today is our ground rules for matrix analysis, particularly the sign convention. Okay. We are considering forces to the right, displacements to the right as positive, and we are considering forces upward and displacements upward as positive, okay? That's going to be really important when we go through the process of defining how this changes for trusses, but just keep that in mind. And another thing to keep in mind is that we do have to operate in consistent units. If we have a little time today, maybe we'll dip our toes into our analysis example. So, sound good? Okay, so let's talk about truss elements in 2D. And so the first thing I'm going to try and do is I'm going to try and derive the spring matrix or the stiffness matrix. Now, if you recall, we've already done a 1D bar element, not an R, that's B, a 1D bar element. And we said that the spring matrix was something like EA over L, and then it was that, right? That's what we said the stiffness matrix was for a one-dimensional bar element, okay? And that's still going to be the case, okay? So if we have a one-dimensional bar element formulation, this is our stiffness matrix, okay? Now, I'm using this term 1D. Why am I using the term 1D? Well, I'm calling this one-dimensional because I'm saying that the bar has 1 degree of freedom at each node. So if you remember, this is the bar, and when we were doing bar element problems before break and for your homework that's due Wednesday, we just have a single degree of freedom at each side. So degree of freedom 1 and degree of freedom 2. Okay? So that's why the matrix is 1 by 2, right? Or sorry, 2 by 2, because there's 2 degrees of freedom with each side. Okay? Does that make sense? And notice how I've drawn the degrees of freedom, and whether it's a force or a displacement, it doesn't really matter. Notice how I've drawn them to the right, because we're considering forces and displacements to the right as positive. Okay? Does that make sense? Everybody good with that? Now, 1D bar elements are great for understanding structural analysis and understanding matrix analysis of structural systems. But the problem with a one-dimensional element is that we don't really use it very often. I mean, you all, for example, in your project, you were analyzing a truss that connected this building to that building. Those elements were two-dimensional, right? Because the elements would be diagonal, right? And they could deflect left and right and up and down, right? Okay? So if we really want to look at a real element, so if we want to look at a 2D truss, so a 2D truss element is going to look something like this. It's going to be like that, and it's going to have, at each node, it's going to have 2 degrees of freedom. It's going to be able to displace left and right, and it's going to be able to displace up and down. Okay? So in fact, the element's going to look like this. Okay, so I'm just curious, if the element looks like this, how big is the stiffness matrix? If this one's 2 by 2, how big is this one going to be?
4 by
4 by 4, right? So let's just see if we can reason through this. So I'm going to use my numbering scheme here that I have on the slide. I have so 1, 2, 3, 4. Okay, so 1 and 3 are the horizontals, 2 and 4 are the verticals. Okay, so let's see if we can reason through what the stiffness matrix would look like. Now, I want to be clear that the difference between a bar element and a truss element is just the ways that the joints or the nodes can move. Okay, it is still a bar, and it still has the same mechanics. Okay, and if you remember truss elements, remember one of our assumptions with trusses is that they can only resist forces axially, right? And the stiffness is defined by EA over L. So I propose we're going to have an EA over L outside here, okay? And we just got to figure out what goes in here, okay? So maybe what I'll do is I'll break out another color here and I'll say, okay, let's see if we can let's do that, okay? And we'll say 1, 2, 3, 4, 1, 2, 3, 4. Okay, let's see if we can reason through this. So, again, the bar element and the truss element have the same mechanics. They are defined by the same mechanical properties. Okay, truss elements or bar elements can only resist load axially. Okay, so let's go back. How did we derive this? How did we come up with this matrix? Do you remember what we did? We took the bar and we actually physically deformed it, right? We took it and we physically stretched it or we physically squished it. And then we figured out what are the forces necessary to make that happen. Okay? So what I propose is that for this truss element, the only way we're going to get a response is if we apply forces along the axis, along 1 and 3. Okay? So here's what I'm getting at. If I take point 2, if I take this and I lift it up or down, I propose that the bar has 0 stiffness. It's just going to freely deform up and down. So what I'm getting at is anything that's associated with a 2 and a 4 isn't going to have any stiffness. Oh, I got that backwards. Anything that's associated with a 2 and a 4 isn't going to have any stiffness. And what's left over? How many cells are left over? 1, 2, 3, 4. How many cells here? 1, 2, 3, 4. That's it. I'm so sure that I'm right that I even have that there on the slide. So there we go. So that's the stiffness matrix for the for a bar element or for a truss element. Okay, it's basically just the same thing here. It's just expanded to incorporate other degrees of freedom. Yes.
That's KE prime.
I'm going to get to that. I'm going to get to that here in a bit. I'm glad you noticed that. Okay, because watch this. Hold on. Boom. You may be wondering about that prime symbol. Okay, because you'll notice it. Yeah. So I put this little KE prime here. Okay, and I'm calling this KE prime, and you're wondering why am I doing that? You might be wondering what's going on with that K prime. For now, just sort of bear with me. I'll get to that here in a bit. But that was there on purpose. In fact, it's not just here. Look here, you can see F1 prime, delta 1 prime. You can see the primes here as well. That's on purpose too. Okay? But assuming everything so far, at least from a base understanding of the mechanics, does this make sense? Everybody okay with this? Okay. All right. Now, let me see if I can sort of explain the real issue between bars and trusses. Okay? And I want to see if I can explain that by looking at stiffness matrices a little bit of a different way. Okay? So follow my logic, my ideas with me for a second. Okay? Remember, how did we come up with this stiffness matrix at the very beginning? Like, how did we get these terms? We took the element and we deformed it, right? We actually took the element and we stretched it and we squished it and we recorded the forces necessary to produce those deformations. And then all we did is just write it in matrix form, and that was our stiffness matrix, right? That's what we did to get this right here, right? Everybody with me on that? Okay. All right, so keep that thought in your head. And also let's look at this. This was our basic definition of stiffness. Like, ignore all the matrix hullabaloo. That if you want to relate forces and displacements, that the force can be the displacement times this term EA over L. And this term EA over L is what we term the axial stiffness. Whether it's a bar or a truss, that would be the magnitude of the stiffness. Does that make sense? Okay, so let me ask you a question. What if delta equals 1? What does F equal if delta equals 1? It equals EA over L, right? Make sense? So here's my point. Could we say that the terms in this matrix are the forces necessary to produce those displacements? Okay? In other words, I want you to sort of think about the terms inside these matrices as forces, but specifically forces under a unit displacement. Does that make sense? Like, if any one of these displacements equals 1, then the force is EA over L, as long as it's axial. Okay, does that make sense? I just want you to think about these terms as forces because that's the problem with assembly, okay? And that'll start to get into why we've got these primes, what's the deal with this T matrix, and so on and so forth, okay? So bear with me. Everybody good so far? So give me a little bit of rope here. We'll see what we can do. All right. So again, I want you to think about these terms as forces, okay? And if you think that, then would a fair statement be that assembly is sort of just force summation? Like, aren't we just summing up forces? I mean, how did we assemble bar elements? What do? We put the stiffness terms where they go in the big old matrix, and anytime those terms overlap, we add, right? That's how assembly worked, right? Anytime the terms overlap, they add. Let's see if we can put a picture on that. See, the problem is, like, when we deal with trusses, and this is particularly true with trusses, the issue is that if all we did was just use this matrix directly, we wouldn't be able to do assembly, okay? And the reason why we wouldn't be able to do assembly is because the forces wouldn't be facing the same way. Like, let me put a picture beside it. Okay, so let's say we had a real simple truss problem. Let's say here's the truss problem, okay? So I've got 3 joints. How many elements do I have? I've got 3, right? So how would assembly work? I would write a stiffness matrix for this element, for this element, for this element, and then I'd assemble it, right? And I'd assemble it the way I would assemble any bar element type system. Well, here's the problem, is that this is what they would look like, right? This stiffness matrix for this element, if I use this, is going to correspond to these forces. But what about the element between 1 and 3? Well, the forces are going to go axially and perpendicular, axially and perpendicular, axial, perpendicular, perpendicular. I guess my question is, how do I do assembly if like these forces and these forces are all facing different directions? Do you see what I mean? That's the problem, okay? The problem is that these forces are all faced in different directions, and so I can't do assembly, okay? So the way that I fix that is I do a transformation, okay? And so that transformation involves taking this system and turning it into this system, okay? In other words, taking each of these sets of forces and rotating them so that now they're all facing the same way, they're all facing the same way, and so when I assemble them, I can just add them directly. Does that make sense? So when I said here, I said, you know, what's the difference between a bar system and a truss system? The difference is that before we do this assembly, we have to do this transformation. And so we have to take KE prime and turn it into KE, okay? That also hopefully explains this whole prime symbol that I've been mentioning, okay? Specifically, if you want to give me give a little bit of rigor to this, what I'm saying is that for a given element, if I look at the degrees of freedom at the end of each joint, I can express them as follows. I can either express them in local coordinates, which is along the element, right? So if I have an element that's sort of like faced this way, I can say, here's degree of freedom 1, 2, 3, 4, okay? There's an advantage to defining degrees of freedom that way. It's because the stiffness matrix is really, really easy to derive, okay? But the problem is that's not really good for assembly, okay? So really what I want for assembly is I want right up, right up. I want them in the same direction for all of the elements. I want them in some sort of global coordinate system to where each element is referenced the same way. So local coordinates are easy to derive, but global coordinates are easy to assemble, okay? Does that make sense? Now the way that we're going to figure this out is we're going to say, okay, we need to be able to transform from local to global. Okay, so really what I need is if I have local forces or displacements, or if I have global forces or displacements, I need a way of figuring out how do I get from here to here. And the way that I do that is through a transformation matrix. Now this transformation matrix looks really daunting. It's going to be really, really easy here in a second. In fact, really the big thing to recognize is that these terms inside this matrix is really just going to be a lot of trig, okay? It's going to be a lot of trigonometry. Actually not a lot, it's actually very little trigonometry. It just gets repeated a lot. Let me show you what I mean. Watch this. This is a lot easier than I think you probably give it credit. Okay, so let's take a look at, I don't know, maybe like my first local displacement. Okay, and whether it's a local displacement or a local force, it wouldn't matter. It'd all be the same thing. So here's an element, and let's say here's the local displacement. We've been doing this whole semester with trusses. What would I do? Take this, split it up into x and y components, right? And how would I split this up into x and y components? I'd say that this equals that times the cosine plus that times the sine. Right? Is that really all that challenging? Pretty straightforward, right? How about for delta 2? Okay, delta 2, here's the element. Delta 2 is going to go up like this, right? So if this is delta 1, this is delta 2, so I'm going to split this up into x and y. But does anybody see a problem with this one right here? What did we say is positive? To the right, and this is going to the left, right? So I propose that we would just put a negative sign on here to indicate that because it's flipped the other way, we got to make that negative. Okay, does that make sense? So we just keep doing this. Do it the same thing for delta 3, the same thing for delta 4. Put all that in matrix form, and that's your T matrix. That's it. Yes?
Is it will be negative delta 2 or negative delta 1?
Sorry, what? Negative delta 1, because the delta 1's going to the left. Yes. But similarly over here with this one, it'd be negative delta 3. Okay? And I propose this is your transformation matrix. Okay? And what is this transformation matrix? It's just a lot of trig. Why are there zeros here and here? Well, there's zeros here and here because if you're transforming delta 1 and delta 2, the other two have nothing to do with that. You're just transforming like this into this and this into this. So the other, where they mix and match, they don't have any interaction. Okay. Does that make sense? Okay. All right. Now I'm going to throw a little bit of a weird observation at you. Transformation matrices have a very peculiar property, and then that property is called orthogonality. Okay. Now, this is very specific to transformation matrices or anything that rotates in general, and that is, this is very peculiar, is that a matrix is orthogonal if its transpose is the same thing as its inverse. That is not the case for most matrices, okay? Orthogonal matrices are very special in that regard. And just to sort of show you what I mean, okay, let's multiply two matrices together to sort of show you. And by the way, I use a lot of shorthand with this, so see how I'm using C's and S's for sines and cosines? I assume that's okay, right? I'm lazy in that regard. But let me show you what happens. So let's just take a really small matrix, a 2 by 2. So let's take this matrix and multiply it by its transpose. So this is going to be a matrix. Let's multiply it by its transpose. So how do we transpose a matrix? We keep the diagonal the way it is, and we flip the diagonal term. So this becomes negative S. This becomes S. Okay. So do y'all remember how to do matrix multiplication? Y'all remember this? So how do we multiply these? Oh, good gravy. We don't pull up the calendar. Okay. How do we do this? Okay. Let's look at this first term right here. So what do? We do that row times that column. So what do we get? We get C squared plus S squared. Is that right for that first one? Okay. What do we get for over here? We get, what is this? Negative sine cosine, positive sine cosine. So maybe like sine cosine minus sine cosine. Is that right? That's the same thing we're going to get right here, right? Right? And then over here, we're going to get, what is this? Sine squared, cosine squared. Interesting. Remind me, what is the sine squared plus the cosine squared? 1. So we got 1, 0, 0, 1, which is the identity, right? This is the only, if a matrix is orthogonal, that's when that'll happen, okay? There's really two famous examples in linear algebra where matrices are orthogonal, and one of them is rotation matrices like this. The other is permutation matrices, but again, this isn't a linear algebra class. So. Okay. All right. Everybody with me so far? Okay. So, the only thing left to fully explain is how do we get from here to here? How do we do this? How do we transform this K matrix, okay? Well, so I'm going to take this one step at a time. Oh, I know what I want. Before I get to this, I want to do some intermediate calcs, okay? I want to be crystal clear as we don't actually need to compute the angle of orientation for an element, and in fact, structural analysis packages often won't figure out that angle. Let me show you what a structural analysis package will do. So if I am modeling a bridge in Mastham, right, and I have two nodes and I have an element between them. Okay, so what do you program into mass stand? What do you put into mass stand? You put the x and y coordinates of this element and the x and y coordinates of this element, right? So I'm calling them XL and YL and XH and YH. So basically like the lower number node to the higher number node. So you know how in mass stand the nodes are numbered, right? So what the package will typically do is just operate from higher to lower. So what it'll do is it'll say, okay, for a given element, I can figure out the change in X and the change in Y, and I'll just say, okay, the higher minus the lower, the higher minus the lower, okay? And if I have delta X and delta Y, I can figure out the length of the element by just using the Pythagorean theorem, right? And if I have the length of the element and I have these two, I can figure out the cosine and the sine by just saying the adjacent over the hypotenuse and the opposite over the hypotenuse. So I never actually need the angle, I can just calculate it directly. And so often structural analysis packages won't even bother with the angular computation, they'll just do this, okay? Does that make sense? Everybody good with this? Okay. All right, now I want to talk about how we get from here to here. And this is going to seem a little convoluted, but remember, the big thing about matrix multiplication is that you can't switch the order, okay? You can't just like take this and switch it. It doesn't work that way. You have to multiply in order, okay? So how do we get from here to here? How do we do that, okay? Well, what I want to do is I want to start with something that we know, okay? And I propose that we know that local forces equal local stiffness times local displacement. And the reason I'm starting here is because we know what the local stiffness matrix is. We know what this is, okay? All right. Now I'm going to transform them, okay? And how do we transform, or what are we transforming? I'm going to transform the forces and the displacements. Because remember we said that the local was going to equal that times the global. And the local was going to equal that times the global. Okay? So I'm going to replace this with that. I'm going to replace this with that. Does everybody see what I'm doing here? Everybody okay with this? Okay. And let's get rid of the parentheses. We don't need parentheses. Okay. All right. So what am I going to do next? Well, I'd like to get rid of this. So what I'm going to do is multiply both sides by T transpose. Okay? So I'm putting a T transpose over here and a T transpose over here. So on the left and on the left, I put a T transpose. Okay? On this side, the T transpose and the T are going to cancel because they're inverses of one another. And so what I've got is a global force equals this times a global displacement. That is how we transform our stiffness matrix. We take T transpose times K prime times T. I'm going to show you something a while. I pulled this up a while back. Let me show you something. I posted this to Blackboard, by the way. Remember when we first started doing matrix calculations? And I said, okay, here was our problem, right? And I said, okay, here's all this practice. And I said, you know, you ought to make sure that you're comfortable with this. And then I told you, here's this problem. And I said, trust me, this formula looks kind of nuts, but I promise you we're going to do it. Well, now you can kind of see what I was talking about. Don't worry, we'll practice a lot of this stuff on Wednesday. I know I'm throwing a lot of theory and matrix stuff at you. We're going to go do a start to finish example on Wednesday to make sure we're comfortable with a lot of this. So what's our procedure? How do we actually go through start to finish? How do we actually do a truss problem? Well, let me show you how this works. Okay, I'm going to pass these out. And by the way, on the exam, I'm going to give you both the bar element handout and the truss element handout. So you're not going to have to waste space on your formula sheet with these. So. the thing about matrix analysis is that there's a lot of theory and a lot of ideas, but when you actually get to apply it, it's actually pretty easy. So, and again, don't worry, I'm going to give you a start to finish example on how this stuff works. So let me show you how we perform matrix analysis for truss members. So basically what I'm talking about now is this is what Mastan was doing in the background. Remember how you build the model and you click the little analyze button and it would just do it? This is what it was doing in the background. So the first thing it would do is it would assemble the K matrix for the structure. Okay. So again, what I was saying here. Now, what that means is that, so for bar elements, we didn't have, there's a few intermediate steps that we didn't have to do for bars, okay? For trusses, we're going to compute a stiffness matrix, and then we're going to compute a transformation matrix for each element, okay? Now, in order to get these terms, we've got to do some intermediate calcs. So we're going to get a delta x and a delta y, which is the change in x and change in y for the element in question. So we'll go from the higher number node minus the lower number node, right? We'll take the length of that element, and then the cosine and sine, again, we won't calculate the angle, we'll just take delta x over L and delta y over L. We'll then take these, transform them into global matrices by T transpose K prime T, right? So this transpose times that times this, right? Which you can do in Excel or any programming language. It's really easy to do. And then assembly is no different. It's the exact same process. The only thing that's worth mentioning is that the matrix is just bigger, okay? So instead of, so if you remember for bar elements, the big old stiffness matrix was n by n because there was 1 degree of freedom for each node, right? Now it's going to be 2n by 2n because each node's going to have 2 degrees of freedom, okay? So it's just going to be bigger, right? What do we do then? We handle our F vector. No different as before. No different. It's the same process. Okay? There's still going to be unknowns where the reactions are, and everything going to the right is positive, left is negative, up positive, down negative. No difference. Same process. What do we then do? We solve for unknown displacements. The exact same process as before. We got a big old K matrix, a big old F vector. Knock out the rows and columns associated with the boundary condition. Solve. Easy. Okay? What's next? Computing the final results. Okay? And how do we get the final results? We take F equals K delta for the reactions, and we calculate a local force vector for each element. How do we get the local force vector? We just have to add another term here. So we do K prime times the transformation matrix times delta. Because we're going to have, basically the idea is we're going to have a global displacement vector for each element. We need to transform it into local coordinates, then multiply it by its local matrix. And when you look at these FE matrices, it's going to be a lot like bar elements. There's only going to be 2 values, and they're going to be equal in magnitude and opposite in sign, just like it was for a bar element. But it'll be like a value 0, value 0. You just take the second value, same way as we did before. Okay? And that's it. That's matrix analysis for trusses in a nutshell. And just so everybody's aware, what we're going to do next time is this. So next time, we're going to do this problem, okay? And we're going to sort of do it by hand. Now, I'll tell you that this is a problem that honestly, using matrix analysis for this problem is, you know, like, what is it, like a sledgehammer for you know, what is it, an ant for a sledgehammer type thing? You know, type thing. What's that? There you go. Yeah, it's way overboard, way overboard. But the idea is that this process for this little truss, it's the exact same process for a gigantic truss or a gigantic indeterminate truss, right? You'll see that it's pretty systematic, pretty straightforward. It's not really even difficult. The one thing that you're probably going to get alarmed by is the process is just long. And so I will Just go ahead and say, right now, you are not going to have to do a full-blown start to finish one of these on final. Just don't worry about that, okay? That's not what's going to happen. You might have to calculate a piece of a problem on the final, but again, my rule of 3, I apply it here too. So, does that sound good? So we'll start to finish this stuff on Wednesday, but for now, just take what we said, let it soak in, and I will see you all on Wednesday.